Cool. So, like I said, this is going to be a little bit shorter. Normally when we do this demo, it's like a 45-ish minute demo. We're going to try and cut it down to like a 30-ish here at the most. Maybe even a little less. And so, the way I pitched this to you guys when you were out on the floor was I was talking about it as a liquid nitrogen demo. And so, what we have inside here is liquid nitrogen. And you guys know what nitrogen is? You guys are familiar with nitrogen at all? Yeah. So it's a element that a lot of us are very familiar with, one that we have experienced a lot in our lives. But we don't normally see it as a liquid, because in order for nitrogen to become a liquid, it has to be very, very, very cold. And so I have here a little thermometer here that's got some temperatures listed on it. And we'll rattle off a few of these temperatures, and we'll talk about them a little bit. So the one I have at the very top here says 212 degrees Fahrenheit. What happens at 212 degrees Fahrenheit? Yep. Yeah, that's when water boils, specifically. Slide it down here, about 32 degrees Fahrenheit. Water freezes. Let's slide it all the way down to negative 129 degrees Fahrenheit. And that is the coldest temperature ever recorded outdoors on Earth. That's in Vostok, Antarctica. There's a research station down there. So that's the coldest outdoor temperature ever recorded on Earth. And we are going to keep sliding past negative 129 and go all the way down to negative 321 degrees. And so negative 321 degrees is the temperature that nitrogen transitions from being a gas to being a liquid. So inside this can here, it is colder than negative 321 degrees Fahrenheit. Which, like I said, is not a temperature that most of us really ever get to experience or fiddle around with. So hopefully, we'll get to experience a few new things here today. What I'm going to do is I'm going to start by just pouring some of this into the cooler here. And as I'm pouring it, take a look at what it looks like. What would that look like? It's just water, right? Here, even take a little bit closer peek at it here. You can see it.
Water.
Yeah, mostly this looks like water. And what's it look like it's doing? Looks like it's boiling, right? And so, first question I have for you guys here. What does it mean for something to boil? What something is doing? What's happening when something's boiling? Yep.
It's trapping air inside of the water, and then it's letting it out quickly.
So, I guess you could kind of phrase it that way. What do you think? What's boiling mean?
So it's boiling. That means it's really hot water.
Yeah, so water boils at 212 degrees. So when we think of boiling, a lot of times we think of stuff that's really hot. But it's not 212 degrees in there. It's, in fact, probably colder in there than it is just in this room, and this is still boiling. So not everything boils at the same temperature. And so we associate boiling with water, so we think of it as that 212 degrees. But this stuff boils at negative 320 degrees. And so you can pour it out, and in room temperature, it starts boiling almost immediately. So that liquid I had in there, it's already gone. It's already boiled. It's evaporated. So when we say boiling, what we really mean is it's something that's going from a liquid into a gas. And it can happen to anything. Pretty much anything has a boiling temperature. And I think we'll fiddle around a little bit here with some other properties of this. Let's take a quick look at it. Check out some other stuff. Here's a good one. Just got a bucket with some water in it here. And what we'll do is we'll take a scoop in there and we'll set a little ambiance here. So when we pour it in there, all of this is coming out. And what do we think this is? What's all this white stuff?
Dust.
Not dust.
Steam.
Not steam.
Gas.
It is kind of a gas, yeah. So I'll give you a hint. It's not nitrogen. What do we think? What's in the air around us all the time?
Smoke.
Smoke? It does kind of look like smoke. So what's happening here is, basically this is cool, and so it's cool enough that it's making the air around it, kind of turn into its liquidy state. And so we're starting to get a little bit wet down here. And so what do we call, I guess we would say this is basically a cloud. What do we call a cloud when it's near the ground? Yeah.
Fog.
Fog. Yep, so we've just made some fog here. And all it is, like I said, is the water that's in the air around us all the time, very suddenly, like the water in it, turning into a form where it's suddenly visible for us. And you can see it's just falling down onto the floor where it wants to be. And we're going to observe a little bit some different properties of things here. We're going to look at how things change when we get them really, really cold. So can you describe that ball for me?
Squishy.
Squishy. Anything else?
Beat up.
A little beat up. We got squishy and beat up. Anyone observe any other properties of the ball? Yeah.
It's strong and maybe it's even cold.
So the ball right now is just the same temperature the room is. We haven't done anything to it yet, but we're going to make it cold.
It's also yellow and it doesn't have any frost or anything.
Yeah, it's yellow. There's no frostiness or anything on it. We had a squishy, yellow, smallish ball. Bounces a little bit. What do you think is going to happen to this ball when we put it in liquid nitrogen?
It's going to freeze up.
It's going to freeze. Okay. Another question here. What does it mean to freeze?
Either to turn into a hard or be super, super cold.
Yeah, when freezing, it's a lot like boiling. It's kind of just the opposite of boiling. So when we say something freezes, what we mean is it's going from a liquid state to a solid state. So the ball is already frozen because it's already a solid. And so it's going to get colder, and it might get, more solid, I guess. But it's already in its frozen state. It's not a liquid and it's not a gas, which means it is currently frozen. So again, one of those things that we tend to think about it in terms of water is you think of freezing as something that has to happen when you're really cold. But really it is something that is, this is frozen, this is frozen, this is frozen. Everything around us that's solid is frozen. Meanwhile, while we're waiting for that, let's try out something else here. Got a ball, got a hoop. And the ball, like just barely, if I really work it, fits through that hoop. And what I want to do is I want to make it so that it's really easy to fit this ball through this hoop. How do we think we would do that?
There's a really small hole that's bigger than the hoop.
Yeah, we could get a bigger hoop.
The hoop is bigger.
Yeah, the hoop's a little bit bigger than the hole is, yeah.
You could try and figure out a way to shrink the ball, aka either melt it or shrink it in a dryer, which can happen with those.
So you think we should heat up the ball somehow?
Or you could also freeze it, which also somehow
Could freeze the ball. Well, all I have here is the ability to throw it in a cold, so what do you think?
You can't put it in heat because then it'll expand.
That's right. So if we put it in heat, most things when you warm them up, they expand. And so the opposite's also true, where if you put something in cold, it's going to shrink. So if I wanted to make this ball fit through this hoop, which one are we going to end up putting inside here, you think? The ball. So let's throw the ball in there. Let's test out our hypothesis. See if the ball gets smaller while it's in there. And this is something that's kind of a cool property to think about, because this is something that we have an exhibit out on the exhibit floor that's very much about too, is when temperatures change and things expand and contract. Did any of you play with the hot air balloon out on the exhibit floor? Where you press the button and the flame turns on and the balloon inflates? The reason the balloon inflates is because when you warm the air up, it expands. It gets bigger when it gets warmer. And like she was saying, the opposite's also true. You cool a thing down, it tends to shrink. And so I expect what we're going to see is going to be correct there, where the ball is going to shrink once we pull it out. But meanwhile, check on our yellow ball that we threw in there. Still yellow, still a ball, still looks a little beat up. I will say it's not nearly as squishy as it once was. And I can't really grab and squeeze it too hard because it's cold and it hurts to do that, but I can assure you it's not as squishy as it once was. Do we think it's going to bounce?
Yes.
Good shot. A little bit, but not really. So yeah, the properties have changed, and I bet you would find that if we had really, really gone in and precisely measured like how what the circumference is of this ball. I bet it's smaller than it was when we put it in there too. It's probably gotten more dense from being in there, but we didn't measure that, so it probably is a little bit smaller. I remember it was one of our observations we made is that it was kind of small, and it's probably even smaller now because we cooled it down. But so I can't hold it for too long. All right, let's try my secret problem. What do you suppose I have in this balloon?
Helium.
Helium, perfect. What do you suppose is going to happen to a helium balloon when we make it very cold?
It is going to shrink.
It's going to shrink. I heard someone over here say it's going to pop. So if it shrinks, what's going to happen to it?
It's going to shrivel up and let all the helium get out.
All the helium's going to get out. It's going to escape. Give it a shot. Meanwhile, our ball's probably done. So our hypothesis with our ball was that if we cooled it down, it would shrink and it would be easier to fit through the hoop, is what we thought was going to happen. Because when we warm things up, they expand, so it stands to reason that when you cool them down, they shrink. And what do you know? We're exactly right. Good job. So, like I said, even just in that couple minutes it was in the cooler there, this hunk of solid metal here shrank enough that it now fits through that hoop pretty easily. And I bet if we leave this like this by the end of the show, I bet I'm going to have a hard time getting it back out through the hoop again because it's going to expand as it gets back up to room temperature again. Let me try that. That'll be a little side experiment I've got going on here. See if I can get that ball out at the end. Do we suppose all materials react to the cold the same way? You know, if we cool something down, is it going to do the exact same thing as everything else does when we cool it down in the same way? What do you think?
Maybe, I think I know something about the balloon.
What's going to happen with the balloon?
So when it shrinks, if it shrinks too, if it like turns to ice, it'll pop.
Yeah, so he thinks that the balloon is going to shrink and then pop. But what I have here is an item called a bimetallic strip. Why do you suppose they call it a bimetallic strip?
Because it is metal and it's bendable.
It's metal and it's bendable. That's right. Good observation of properties there. But the word bi is a Latin root. It means two. So if you break it down, it's a two metal strip. So this is a piece of metal that's actually made out of two separate metals that are kind of stuck together in the middle. And so I have one side that is brass over here, and I have one side that is steel over here. And now we're going to throw this in the liquid nitrogen. And the hypothesis I want from you guys is, what do you think it's going to look like when we pull it out? What's going to happen when we throw this in there?
One side's going to be smaller than the other because one side shrinks faster.
One side's going to be smaller because one side shrinks faster. So what's that going to look like in terms of the whole strip? Is it going to just like shrink like this? Like, how is it?
It's probably going to look something like this or this.
All right, so he's doing a gesture kind of like this, where he's thinking that like one side's going to recede down more so than the other one is. Any other ideas what we might think happen when we put a bimetallic strip into our liquid nitrogen? Like I said, it's brass and steel. What do we think? I'm seeing a hand gesture over here that looks like a snake striking. Let's try it out. Let's throw it in there. Meanwhile, let's do a little bit of coaxing of our balloon here. Turns out, helium balloons also float in liquid nitrogen. So we gotta kind of force it down. That's kind of an interesting sound it's making. It wasn't making that noise when I put it in there. It sounds like a potato chip bag now. Oh. So it got a lot smaller. You were right. It did the same thing that our previous thing that we put in there did, and it shrank. But what we're finding is that when the balloon shrinks, it doesn't float anymore. Remember when I put it in there, it was floating up on the ceiling. I had to drag it down and throw it in there. When I pull it out, it no longer floats, except, give it a few seconds, and lo and behold, it's going to work its way back up there. And so again, this is basically the exact same thing that's happening with the hot air balloon, where you heat it up, and as the temperature increases, it doesn't all just like suddenly shoot up all the way to the ceiling all at once. it's got to work its way up a little bit. And that's because even in a room like this, the air is less dense up here than it is down here, so it's got to work its way all the way up through that density profile to get all the way up to the ceiling. So as it warms up, the helium gets less and less and less and less dense, and it works its way slowly back up to the ceiling because it's now less dense than the air all the way up there. Try one other thing. Try a helium balloon. Let's try a normal blow-it-up balloon. So what do we have inside this now? Yes?
Air.
Air. And some very special air. Air that only comes from one place. This is air from my lungs. This is air from Ryan's lungs. And we're going to do the same thing we did to that helium balloon. We're going to toss it into our liquid nitrogen. And meanwhile, we'll pull out our bimetallic strip. And you're right, one side did shrink faster than the other one, but the resulting shape is not quite what you thought it was going to be. Like I said, it's more what we were thinking over here with our kind of arched over shape. Yeah, it bent. Because you're right, exactly what happened is what you said was going to happen is the brass side shrinks faster than the steel side does. So as this brass side shrinks, it stays attached to the steel, and steel has to kind of arch over to keep itself attached because it's longer now. And this is kind of a cool thing because this is something that a lot of you probably have inside your houses, especially if you have a little bit older houses. This is how a lot of old thermostats work, is basically they rely on a strip like this, and as the temperature in the room increases and decreases, the strip bends and it either opens or closes the circuit in order to turn the heat on and off. So something that you don't really see that much anymore in like really current systems, but if you have a little bit older thermostat, there's just one of these guys inside of it. That's basically all that's powering it. Is one of these strips. And it's something that's really important to think about. You can imagine if you're something like engineers designing airplanes, you want to know that your different metals are going to react, how they're going to react to different temperatures, because it might be 120 degrees down in the tarmac, and then it's going to be 0 degrees once you get up into the sky, and you don't want this happening to your plane wing when you're up there. And I'm hearing some noises coming out of our balloon already in there. This one's working a little bit quicker than the helium one did. It sounds pretty much the same though. So there's my breath balloon. And something that's kind of cool with that is if you look in there and you catch it in just the right light, you can maybe see a little bit of liquid forming in the bottom there. And that is all the liquid that was in my breath that turned it back into liquid and fell out of it. And as it warms up to room temperature, that stuff goes back away and it reinflates. I'm going to try one other thing here. I'm going to throw this right back in there. And I'm going to pull out my old jar here. This is a trick that I am famously bad at actually doing properly, so we'll see how it goes. But I am going to try and put this balloon in this jar. Shrink it down a little more. It's hard to keep your hand in there. It gets cold in there pretty quick. So I have now a balloon in a jar that is going to be slowly reinflating to the point where it is not going to fit back out of that jug. Gonna be wedged right in there. Perfect. That's how I want it. Maybe. And so, next step is we gotta get it out of there. And I don't want to pop it. I want to keep this balloon. And it might be a time when I may be doing multiple of these shows, and I don't want to have to use a new balloon every time. So I gotta come up with a way to get that balloon back out of there. And so, how do you suppose we're gonna do that?
Either put the jar in liquid nitrogen and face it top down, or put liquid nitrogen in the jar.
Yeah, I could maybe try and dip it in like this and work it down, but the jar is going to shrink along with the balloon. It's probably not going to shrink as much, but it will shrink a little bit. It doesn't really fit in there sideways either. But you said we can put some liquid nitrogen in the jar which is an interesting proposition. It's kind of tricky to do just because, you know, our balloon is currently occupying the top of the jar. But what you're right is that we can do is we can use a whole bunch of nitrogen. And if we can get a little seam under there, we'll pop right out. So what's happening there? Why'd that balloon come out? Yeah.
Because it shrank enough that it could go up and out, and it was trying to force itself out.
Yeah, so basically what happened there is we shrank the balloon a little bit, just to the point where I could get some nitrogen up underneath it. And then what happens when the nitrogen goes from a liquid to a gas is it expands. So a bunch of nitrogen forms, a bunch of gaseous nitrogen forms underneath it, and because the gaseous nitrogen takes up more space than the liquid nitrogen, it pushes itself out and it takes the balloon with it. Now let's see that in a little bit different way here. So I'm gonna get out of here, I'm done with you. Use my jug here. There's just water in that jug. I'm gonna take a look at our ball here. You'll see some frost is forming on the side of it now. I'm going to take some nitrogen and I'm going to pour it into here. Uh-oh. Good enough. Not the prettiest balloon I've ever blown up, but hey, we'll take it. So, the question is, what is inside this balloon? Yes?
Nitrogen gas.
Nitrogen gas, what do you think?
I think the water got freezing cold, and then added, and then once there was this part was so small, and then it was and it all the way to here.
Yeah. So yeah, the gas filled it up, and you're right, it is nitrogen gas. So what is in here is pure nitrogen gas. And I think my balloon probably has a hole in it because it's shrinking rapidly on me, I'm noticing. And so the question I have for you guys is, what do you think would happen if I were to inhale this? What do you think?
It's very toxic, and you will get very sick.
Think it's very toxic, and I will get very sick. What do you think?
I think it will pop.
You think it'll pop if I try and inhale it? So who thinks it's very toxic and I'm going to get very sick if I inhale the stuff in this balloon? Few of you, handful of you. How many of you want to see me try it anyway? Some of you. It's a good way to tell how well I'm doing in this show. People think that if I inhale this, I'll get sick. Well, anything for show business. Not sick yet. My voice didn't change. I didn't freeze up. A lot of times people assume that like my lungs are gonna like freeze if I do that. But I'm feeling completely fine. I mean, we can check back up on me in an hour. We're open till 5 today, so check back up at me at 5 and see how I'm feeling. But for now, at least, I'm feeling completely fine. Nothing particularly has changed with me. And that's basically exactly what I expected was going to happen. And so, I guess to explain this, why don't all of us just take a big deep breath in here. Just in and out. What did you guys just inhale? Air. And air is made up of a bunch of different stuff. And so the stuff we generally think about when we think of inhaling air is we think of oxygen, because that's kind of the thing that we get out of the air that we really need to use a lot of. But the truth is, oxygen only makes up maybe 18 or so % of the air. The other 82% of it, most of it's nitrogen. About 4/5 of what you just breathe in there was just pure nitrogen anyway. So it's in the air around us as a gas all the time, and so this really wasn't all that different from the air I'm just breathing in all the time. Yeah.
And maybe even about the balloon, when like that water, when it got so cold, and then all the shit turned white, and then it blew the balloon up.
Yep. So yeah, the nitrogen went from being liquid to gas, and like I said, it got bigger and it blew the balloon up. Alright, just got a couple more things for you here. Something in here already? What did I throw in here? Nothing. Alright, so what we'll do is take a look at these two things here. I'm sure you guys recognize these. Something we see all the time. Yeah.
Coin.
They're coins. Very specifically, they're pennies. And so I have 2 pennies here, and can you read for me the year on that penny, and you read me the year on that penny? Oh, I kind of got you in the dark back there. I normally wear glasses, but I don't wear them when I got the mask. 1937. I think it's 1967, but and that one's a 2020. So we have one, either 1937 or 1967. I said I can't really read it that great either. And we have one from 2020, brand new. And so what we're going to do is we're going to throw these 2 pennies into the liquid nitrogen. And what do we suppose is going to happen between those 2 while they're in there? Thinking hard. What do you think?
I think maybe you'll hear a sound of while they're being cold. Maybe.
They're gonna make a sound while they're in there?
Cracking sound.
Yeah, that crackling sound, kind of like the balloon did. Okay, it's a good hypothesis. What do you think?
It's gonna I forget.
Hey, it happens to the best of us. What do you think?
I'm just putting my hand on the back of my head.
All right. You got another guess?
Shrink.
I think it's gonna get straight. Is that what you said?
No, shrink.
Shrink. I like that. Make sure all my tools are working here. All right. Let's give it a shot. So remember, we have 2 pennies, one from 1920, or not 1920, 19, I think it was 67, and then one from 2020.
67 or 37.
67 or 37. So that's our old penny. That's our new penny, as soon as I get it out of here. And I'll tell you, I'm about to whack these 2 with a hammer. What do we suppose is going to happen when I whack them with a hammer? Yeah.
They are either going to shatter or nothing is going to happen.
So they're either going to shatter or nothing is going to happen. Those are 2 pretty big, let me leave that in there for a little while since we're going to talk a little bit more. I don't want it to warm up. Pretty big difference. Either nothing or they're going to shatter into a million pieces. Why do you suppose I put 2 of them in there?
Because there might be different results.
There might be different results. So what do we think the result is going to be when I hit it with a hammer? Do we think they're both going to shatter? Do we think neither of them are going to shatter? Do we think one's going to shatter? What do we think? Do you think something else entirely is going to happen? What do you think?
I think the older one is going to shatter.
So he thinks the older one is going to shatter. Who thinks that the old penny is going to break when I hit it with a hammer? Who thinks that the new penny is going to break when I hit it with a hammer? Hopefully think the new one. Who think both of them are going to break when I hit it with a hammer? Who thinks neither of them are going to break? Who just likes raising their hand? Alright, we'll try our old penny first. Our 19-something-y-7 penny. A little dense, but it's mostly okay. It's cold. Alright, let's pull the new one. So, our hypothesis that the old one will shatter is not happening, but we could still get neither of them, or we could get the new one to shatter. So this is our 2020, our brand new penny. Keep an eye on that, because those are sharp. So yeah, our new one broke. And why do we suppose that is? Why would the new one break and the old one not break? Yeah.
Maybe they're different kind of metals.
Maybe they're different kinds of metals. What are pennies made out of? Copper. And you're mostly right. For most of history, pennies were made out of copper. That is until 1982. In 1982, the price of copper was such that a penny became more, the amount of copper in a penny was more valuable than a penny. So they switched from making pennies out of copper to making them out of a different metal called zinc. And so they just coat it in copper now. So there's a really thin layer of copper on the outside, but it's all zinc in the middle. And you can even see if you look at the inside of this, you can see it's that nice copper color on the outside. It's actually gray or almost black in the middle. Like I said, it's made out of a different metal. And you guys can come up and get a closer look at this once we're done here. But And you can see it's different color on the inside than it is on the outside. And so, like I said, the reason they did that is because zinc is a lot cheaper than copper is. And so zinc doesn't react the same way to cold that copper does. Zinc gets really, really brittle when it gets cold in a way that copper really doesn't. And so these old pennies, I'll say, this is a 1967 penny, because I'll say I've used this penny a bunch of times before. This is a... That penny's done this demo probably more times than I have, because it keeps being okay. I'll get it back later. And meanwhile, our zinc penny, like I said, shattered into a million pieces here. And so, I think we will kind of call that a wrap here. Actually, we'll do one more thing. The problem with liquid nitrogen is that we got to buy it kind of in a large quantity like this, and so we got to use it while we got it, because even in a big, heavily insulated container like this, it does evaporate. And so we don't have another show where we're using liquid nitrogen for a while. And so, there's a little left in there. There's maybe enough for one more show in there. But I'm not going to put my stuff I've been using back in there, because it's just going to evaporate probably. And we'll do one more big dump of our nitro here so you can kind of watch it all evaporate really, really quickly. And it's gone. And you'll probably notice a couple little kind of ice balls moving around here. So what you're seeing there is actually the same thing that happens, like, you guys ever pour water on like a hot stovetop and you see those little balls of water form? Same thing is happening here. It's just happening at room temperature rather than at 400 degrees or whatever your stovetop is at. But that's going to be it for the show today, so thank you guys all for watching. Thanks for hanging out with me. Like I said, if you guys want to check out the penny or anything else in here, I'd be happy to explain something a little more to you. But for our audience online, again, thank you guys for watching. The Headwaters Science Center is open. We're open 7 days a week, so Monday through Saturday we are open 9:30 to 5. Sundays we are open 1 to 5, so swing by after lunch on Sundays.